So you should now know that a complex number always has a real part and an imaginary part. And so the two of those together form what we call a complex number. Now, if you have two complex numbers, one over here and one over here, the only way those complex numbers are actually equal to one another is if the real parts are equal and also if the imaginary parts are equal. So let's go through a few examples of what I mean by that, and then we're going to get into simplifying some expressions involving multiplying and adding complex numbers. So let's say, for instance, I tell you, I mean, this is kind of going to be a little bit trivial, but I just want to make sure you understand. If you have the complex number 2 plus 3i, you have that over on the left hand, and you have another person or somebody has some another complex number 2 plus 3i, and I ask you, are these numbers equivalent? Well, I think you would all tell me yes. How do you know they're equivalent? Well, the only way these are actually truly equivalent is if the real parts match and if the imaginary parts match. If there's any mismatch, they're not equal. So those are actually equal. If somebody has negative 2 minus 4i, and on the other hand, they have negative 2 minus 4i, you see what I mean? It's pretty simple here. The negative 2's match completely, the negative 4i's match, so these are equal. Those are complex numbers that are equal. If somebody has 6 minus i as a solution to an equation, and somebody else has 6 minus i as a solution to an equation, the real parts and the imaginary parts exactly match, so that's a solution. Or, excuse me, not a solution. They're exactly equivalent to one another. And then the last one here is, even if you involve fractions, it's the same thing. 1/2 minus 3i over 2, and then somebody else has a complex number 1/2 minus 3i over 2. The 1/2's match and the negative 3i over 2 completely match, so these guys are completely equivalent to one another. But let's change it up a little bit and say, well, what if I give you, if one person has 2 plus 3i as a solution, and then I have 2 minus 3i? A lot of students will just say they're equal because the 2's match and the 3i matches, but notice the sign is different. These are different, so these are not equivalent to one another. So you need to know when two complex numbers are equivalent, and the only reason that they are is if they completely and totally match, including the sign in the middle. What if you have negative 2 plus I on the one hand, and someone has 2 plus I over here? Well, the negative 2 does not match the 2. The i's match, but the 2 and the negative 2 don't, so these are not equivalent to one another. Moving right along, what if we have 1/2 minus 2i? And on the other hand, somebody has 1/2 minus 2i. 1/2, well, these are actually equivalent. Let's say we have, let's make it like this, 1/2 plus 2i. Well, these are not equivalent. So we have the 1/2 matches, but this is a negative 2i, this is a positive 2i there. And then if we have, so they don't, they're not equivalent. What if we have 3/4 plus 1/2 I, and someone here has 1/2 plus 3/4 I. Sometimes students will get confused and they'll say, well, this real part matches this imaginary part, and this imaginary part matches this real part, so they're equal. Well, of course they're not equal. The only way they're equal is if the real parts are equal, and then separately from that, the imaginary parts have to be equal. So that's pretty trivial stuff, but I want to give a couple of examples to let you know, because none of us are born understanding what a complex number is. The only way they can be equal is if the real parts exactly match and the imaginary parts exactly match, including the sign. That has to match too. So now we're going to do some examples of very simple addition and multiplication of complex numbers. So if I have a complex number, 9 plus 2i, and I have another complex number, 1 minus 7i, and I'd like to add them together, what do? Well, basically what you do is you kind of pretend that this I is basically like a variable, because you know how to handle this if I is just a variable. Like if I was x and this was x, you already know how to do it because you know about like terms. You can only add things together if they're like terms. So you can add the coefficients of I together, and you can add just the numbers together. But of course, I is not really a variable, but you treat it the same way. The only way you can add those imaginary parts is if they both have an I. The only way you can add the numbers is if they're just pure numbers. You can't really add real parts directly to imaginary parts because they're not like terms when you think about it. So what we have here is we're going to add these real parts. 9 plus 1 is going to give me 10. And we add these imaginary parts. 2 minus 7 is going to give me negative 5. But it's not negative 5, it's negative 5i, because that's what I'm adding together. And this is actually the final answer. So adding complex numbers is really, really simple. You just add the imaginary parts, you add the real parts, and you're done. What if you have 9 plus 2i, right? And you're going to add to that just a purely imaginary number, 3i. Some students look at that and have no idea what to do. But then you realize this is just a complex number, but the real part of it is just 0 because it's purely imaginary. So you add the real part of this to this, but it's 9 plus 0, so you get 9. And then you add the imaginary parts, you get the 5i back. 9 plus 5i, that's the final answer to that problem. And similarly, you can have 9 plus 2i as a complex number, and I can add, instead of adding a purely imaginary number, I can just add a pure real number to it. So I add the real parts together. 9 plus 6 is 15. I add the imaginary part to the imaginary part here, but it's the imaginary part of this number 0, so I just keep it as 2i because I'm just adding 0i to it. So you get 15 plus 2i. So it's really, really very simple. You just treat it as if it's any other algebraic expression and go from there. What if I have 5 minus 7i, and I'm going to subtract 8 plus 2i? Again, if this was just an expression, you would know what you have to do. You have to distribute the negative in to both of those terms, and that's what you have to do in this situation too. So you can take the parentheses away here, 5 minus 7i. The negative goes in, making negative 8. The negative goes in, making negative 2i, and then you basically collect like terms. The real part is going to be 5 minus 8. 5 minus 8 gives me negative 3. And then what you have left over, just for completeness, what you have left over is the negative 7i and the negative 2i. And I can now add these together. Negative 3, what's negative 7 minus 2 is negative 9i. So you get negative 3 minus 9i. All right? We just have a few more problems to kind of increase the complexity, but none of these are going to be really difficult at all. Now we change it a little bit and we say, what if we have 3 times the complex number, negative 2 plus I, and then we subtract 4 times the complex number, 3 minus 2i. How would you handle this if this wasn't a complex number? Well, you would distribute the 3 in, you distribute this negative 4 in, and then you collect like terms, and that's all you're going to do here. So you have 3 times negative 2 is negative 6. 3 times I is 3i. This is negative 4 times 3 is negative 12. Negative 4 times negative 2 is positive 8i. And then you collect terms. So the real part is negative 6 minus 12 gives you negative 18. But I still have these imaginary things, so I'm going to keep them along for the next step. And then finally I have, what's 3 plus 8 is 11i. So you have negative 18 plus 11i, and that's the final answer there. All right, we only have a couple more problems. Now here is where a lot of students start getting confused, and I understand why, because it's not obvious until you deal with this stuff a lot. But what if you have I times 3 plus 4i? Sometimes students will get really confused, like, well, I have an I out here. What do I do? I've never seen a problem where I have an I out there. You follow the rules of algebra. This I is a number. It's just not a real number. So it has to distribute into the 3, and it also has to distribute in here. So when you take I times 3, what you're going to get is 3i. And I times 4i is going to give you 4, but the I times I gives you I squared. But you now know that I squared is always negative 1. So anywhere you see that, you have to replace the I squared with negative 1. So you have 3i minus 4. And we always want to flip it around so the real part is first. Negative 4 plus 3i. So you have the real part first, the imaginary part next. And this is the final answer. So if you ever have to distribute things in, you do exactly the same as you always do. But anytime you have I squared, you got to substitute for negative 1 and go from there. All right? Last two problems. On the outside, what if I have negative 4 times I, and on the inside, negative 2 plus I? Well, I have to distribute this in, just as I always would. So the negative 4i times this, the negative times negative gives me a positive. 4 times 2 is 8, and then you have the I there as well, so it's going to be positive 8i. But then when I do it here, negative times positive means I'm going to have a negative. 4 times 1 means 4, and I times I is I squared. Don't try to do too many things at once. Write the I times I as I squared. But in the very next step, you know that it's going to be negative 1. You have to replace this with negative 1. So you have 8i plus 4, but we always like to flip it around so the real part is first. 4 plus 8i. Answer is 4 plus 8i. Okay, the last problem we have is a little more complicated, but not too bad. What if we have 3 minus I times 3 plus I? 3 minus I times 3 plus I. A lot of students look at that first and say, what do I do? But I'm trying to tell you, basically treat I as a variable, so you're going to do FOIL on this. It's not a variable, of course, but you treat it as if it is, so we do FOIL on this. The first terms multiplied together, 3 times 3 give me 9. The inside terms give me 3 times negative I, give me negative 3I. The outside terms, 3 times I, give me positive 3I. And the last terms, you got to be careful. Negative times positive gives me negative, but I times I gives me I squared, like this. A couple of interesting things happen here, though, because notice you have a negative 3I and a positive 3I, so these actually add together to give me 0. And also, the I squared is going to give you a negative 1. So you got to be careful with the signs. You have 9. Ignore all this because it's 0. The minus sign is still there, but the I squared is replaced with negative 1. Don't do too many things at once. Write it as 9 minus and replace this negative 1. So you get 9 plus 1, so you get 10. So the answer is actually 10. So the interesting thing is, a couple of things I want to talk to you about, is that you can have a complex number multiplied by another complex number, and the answer that we got is just well, it's a complex number because all numbers are complex, but it's purely real. There's no imaginary part to it. And that's kind of one of the things I was telling you early in the beginning. Complex numbers are so useful because a lot of times we get the answers out of the equation in complex form, but sometimes we'll combine equations together or multiply it by something else, and we might not get a complex answer. We might get a purely real answer. So some students say, well, why do I care? Well, it's hard to explain without you getting into more advanced math and me showing you solutions to really advanced equations. But this is the crux of it. A lot of times we multiply these complex numbers together and we get real numbers back. So even though it seems like they're useless, they're not useless because they often combine to give us real numbers. The other thing I want to tell you about is I want to point out something to you here. The 3 plus I is what we call the complex conjugate of this. So 3 plus I is what we call the complex conjugate of 3 minus I. In fact, they're complex conjugates of each other. So a complex conjugate is very, very similar to what we already talked about. We already talked about the the conjugate of a radical. So if you have something plus something and there's a radical involved, to make it a conjugate, you just replace the sign in the middle, flip the sign from a negative to a positive or positive to negative, and that's called a conjugate. We use that all the time to clear the radicals from denominators, right? But don't forget, I is really a radical too. I is the square root of negative 1. So we have the thing called a complex conjugate. So anytime you have a real plus an imaginary part, you just flip the sign of the inside and that's its conjugate. Or if you start with this one, you flip the sign of the negative. This is the conjugate of this and this is the conjugate of this. They're conjugates of each other. Basically, there's peanut butter and jelly. They go together. But the idea is when you multiply a complex number times its conjugate, you will always get this cancellation in the middle and you'll always get an I squared, so you'll always get a real number. So in the next few lessons, we're going to use that because we're going to use it to clear away any imaginary numbers in the denominator of fractions by multiplying by the conjugates. Just like we multiplied by the regular conjugate for radicals to clear the radicals, we're going to end up multiplying by the complex conjugate to get rid of any i's, any imaginary numbers in the denominator of fractions. So this is what a complex conjugate is, and the property of multiplying a complex conjugate or a complex number times its conjugate will always give you a real number. That's true for any conjugate pair like that. So this is the idea of multiplying and adding complex numbers in algebra. Make sure you can do all of these. Follow me on to the next lesson. We'll increase the problem complexity to give you more practice, but ultimately we're going to solve all the problems the same way. So follow me on the next lesson. We'll do it right now. Learn anything at mathandscience.com.